Myself Zaryab Khan. Today I am going to present my research presentation, which is supervised by Associate Professor Dr. Salma Khan, Department of Physics, Abdul Khan University, Mardan, and co-supervisor is Associate Professor Dr. Nasir Rahman, Department of Physics, University of Lucky Marwat. My research topic was a DFT study of structural, electronic, elastic and optical properties of gallium beryllium trichloride and gallium calcium trichloride. So first of all, we have to look at this perovskite structure, in which we have gallium from group 3rd of the periodic table, which is post-transition metal, and X represent here two elements, which is beryllium and calcium. Beryllium and calcium are from the group 2nd of the periodic table, which is alkaline earth metals, and the third one is chlorine, which is from the halogen group 7 of the periodic table. So these three elements form a perovskite structure, and the aim of this research work is to study the structural, electronic and elastic as well as optical properties of this compound. Moving on, we have outlines in which we have introduction about perovskite and its different types, and second we have motivation, that why we use perovskite structure and why it is a good option to use it in different electronic devices. Then we have theoretical formulation of density functional theory, that why we use density functional theory for many body system rather than Schrodinger equation. Then we will discuss aims and objective of this research work, that why we are performing this research and which property of the material we will have to find. Then we will discuss about the computational work, that what type of computational work is being done and what type of code we have used. Then we will discuss the results of this material and this research work, and at the last we will conclude this, that what is the relevancy of this material. Now we will discuss it one by one. So the first is introduction. In introduction, we will discuss perovskites, that what is perovskites. So actually perovskites are a material having a crystal structure as calcium titanium trioxide. Now perovskites are of different types. So the most common type of perovskite is general halide perovskites, having a chemical formula ABX3, in which A and B elements can be metallic cations, which can be alkali metal, alkaline earth metal or transition metal, and the X atom represent the anion. Here we have a crystal structure of general halide perovskite, in which the purple color atoms represent the alkali metal or alkaline earth metal. Similarly, the blue color represent the alkali metal, alkaline earth metal or transition metals, but the green color represent the anion atoms, which is mostly fluorine or chlorine or any other atom. So perovskite structures are very important in different applications and have many applications in different electronic devices. These materials have a wide scope of applications due to its physical and chemical properties. Now the classification of perovskites. So perovskites are classified into two major groups, which is inorganic oxide perovskite and halide perovskite. So inorganic oxide perovskites are actually a very attractive compound and have a wide variety of applications due to its large number of atoms in a compound. For example, we have a materials CH3, NH3 and PBl3. This material is inorganic oxide perovskite and have exhibit both physical and biochemical characteristics, such as it is utilized as catalyst due to its sensitivity in the reaction. Then inorganic oxide perovskite is further divided into intrinsic perovskite and dot perovskite. To be very honest, I didn't find any literature on intrinsic perovskite. I'm still working on it, but the dot perovskite is actually a class of perovskite in which a chemical doping is performed, and it is actually a strategy to prepare a highest efficiency and stability based solar cell. Another class of perovskite is halide perovskites. Actually, halide perovskites is an outstanding photosensitive class of the perovskite, which is widely used in lasers, photocells, photodetectors, solar cells, light emitting diodes, photodetectors, and X-ray scintillators. The halide perovskites are further classified into alkali halide perovskite and organometal halide perovskite. So alkali halide perovskite is actually a combination of most electropositive and most electronegative elements. As we know that alkali is most electropositive and halide is most electronegative, such as chlorine. So alkali halide perovskite has a chemical formula of AbX3 in which A and B element represent the metallic cations, which should be alkali metals or alkaline earth metal or transition metals, and the X atom represent the anions, which should be fluorine or chlorine or something else. Now the second class, which is organometal halide perovskite, is actually a combination or sort of organic inorganic hybrid system which shares the structure AbX3, in which A is the large organic cations and B is the small metals cation, and X is of course the anion, which is halide. Moving on, we have fluoroperovskite materials, which is very important and most complex perovskite structure, having a chemical formula of AbF3 in which the anion atom is fluorine atom, and the A and B atoms represent the metallic cations, which is alkali metals or alkaline earth metal or transition metals, and fluorine represents the fluorine anion. Now the motivation behind the use of perovskites material. So actually perovskite material possess chemically and mechanical stability. Apart from that, fluoroperovskite have a wide band of energy, whose band gap varies from narrow to wide due to which its application can be deemed in many electronic devices like solar cells, photodetectors, light emitting diodes, lasers, and memory storage devices. Similarly, due to the perovskite's chemical and mechanical stability, it have a long term stability and superior charge transport and high crystallinity. Moreover, perovskite solar cells are thought to be the future of solar cells or solar power, which can be used to meet the demands of energy in futures. Apart from that, fluoroperovskites are very attractive candidate for optical devices just because of its wide energy band gaps, and due to this it's play an important role in the absorption of ultraviolet light. So we can use these type of materials in ultraviolet filters. A fluoroperovskite having a narrow band gaps are promising thermoelectric materials. So if we have a material having a narrow band gaps, then it is a good thermoelectric material, and of course it is very good for scintillating material as well. The theoretical formulation of density functional theory. First of all, the background of wave mechanical quantum physics was first invented by Schrödinger equation. So we have Schrödinger equation for many body system in this case, because in this case we don't have any one hydrogen atom for which we have to find the Schrödinger equation. We have gallium, beryllium, and chlorine. So it is a many body problem. So in this case the Schrödinger equation will be, first of all, we have the total Hamiltonian, which is equal to the kinetic energy of electrons and plus the potential energy of the electron. So in other words, we can say that the Coulombic attraction between two electrons plus the kinetic energy of the neutron plus the potential energy between two nucleus plus the potential energy between nucleus and electron. So this make up the total Hamiltonian of the system. When we expand this Hamiltonian, we will get minus summation h cut square del square divided by 2m, and this mass is the mass of the electron because this is the kinetic energy of the electron, plus the potential energy between two electrons will be represented by half summation e square divided by mod of Ri minus R of I prime, minus the kinetic energy of the neutron is represented by minus h cut square summation h cut square del square divided by 2mj. This m is the mass of the nucleus or the mass of the neutron, which is represented by capital M. Plus we have another term which is the contribution of Coulombic attraction between two nucleuses, which is half of summation Z and Zj and Zj prime E square divided by capital Rj minus capital Rj prime. And the last term is the potential or the Coulombic attraction between the nucleus and electron, which is represented as minus summation Z E square divided by small r I minus capital R J mod. So this make up the total Hamiltonian of the many body system. Now if we derive the total energy of the system, so we will use eigenvalue equation. So we have Hamiltonian, total Hamiltonian, which is this one, and if this Hamiltonian operated on some wave function psi, which is a function of r and capital R, it will give us the total energy of the system and the same wave function, which is a function of r and capital R. So this type of problem in which we have different contribution of these terms, this is very complicated to solve using Schrodinger equation, because this is not the simple case like a hydrogen atom. So for this purpose we cannot solve this type of problems using Schrodinger equation, so it is complicated to solve. So for this purpose Hohenberg and Sham gave two theorems on which density functional theory is based. Now what is density functional theory, DFT? Density functional theory is actually a quantum mechanical method to treat many body problems. Now in Schrodinger equation we have atoms like hydrogen and around this we have electron, but in density functional theory we have electron density instead of electrons. So we use electron density in density functional theory to show the specific distribution of electrons in a crystal or a material. So in density functional theory main factor is the electron density. Now the modern density function theory relies on the grounds of two eminent Hohenberg and Cohen-Sham theorems. So the first theorem states that the external potential, or we can say that the ground state energy, is a unique functional of the electron density. Now what is the meaning of the functional? So functional is actually the function of a function is called functional. For example, we have the n of r, which is the electron density in this case, and this n is the function of r, and then e is a function of n of r. So actually e is the functional of electron density. So the first theorem states that the ground state energy is the unique function of the electron density. Now the second theorem states that electron density that minimizes the energy of the all functional is the true ground state electrons density. So E of n of r should be greater than E ground state energy and the ground state electron density. Now in density functional theory there is a lot of contribution of different scientists, which is for example Max Born or Robert Oppenheimer or Cohen and Sham. Max Born and Robert Oppenheimer gives the approximation which is called Max Born-Oppenheimer approximations, according to which the nuclei or the nuclear movement is quite minor in comparison to the electron motion, because the nucleus mass is very heavy as compared to the electron. So we can say that the nuclei are more stationary, so the kinetic energy of the nuclei is zero, for example. Then the total Hamiltonian will becomes the equals to the kinetic energy of the electron plus the Coulombic interaction between the electrons plus the Coulombic interaction between the nucleus and the electron. So the kinetic energy of the nuclei is zero in this case. Then Cohen and Sham give us equations. So the main agenda for DFT interpretation is provided by these equations. Actually they says that the electrons in many body systems will work as electrons density, and the only way to resolve the complex arrangement of electrons is to find the exchange and correlation functional value. In general, exchange and correlation functional value is equals to the kinetic energy of the electron plus kinetic energy of the nucleus plus the Coulombic interaction between the different electrons minus the Harte energy J of k. But the problem is that using the Cohen-Sham equations or ab initio calculations, we cannot find or we cannot solve the appropriate exchange and correlation functional value. Actually, in exchange and correlation value, the exchange relies on the electron spin states and the correlation exemplifies the electron's energy. Sorry, the electron exchange due to Coulombic interaction. So for this purpose, various approximations was introduced to solve the exchange and correlation functional value. So the very first in this case is local density approximation, and the second one is generalized gradient approximation. So local density approximation is a well developed and frequently used approximation for, let's say, we have electrons gas system. So for this, so in this case the electron density is constant, so we will have E into electron density, so the electron density is constant in this case. Apart from that, local density approximation has a great impact on uniform system, but for non-uniform system it is totally inconsistent. So a new approximation come up which is called generalized gradient approximation. So for generalized gradient approximation, there is a new term of gradient potential which was introduced. So we can use generalized gradient approximation for non-uniform system to find the exchange and correlation functional value, and for this purpose a new gradient potential of exchange and correlation value was introduced, which is acceptable for non-uniform system. Other than that, the generalized gradient approximation is speedy as compared to the local density approximation, or in other words we can say that generalized gradient approximations outperform LDA in speed. So all these are the computational, or we can say the theoretical formulations of density functional theory. The aims and objectives of this research work. So the aims and objective of this research work is to investigate different properties of perovskites of the type GAXCl3, in which X represent beryllium and calcium atom, using density functional theory inside Win2Gas software. Now the main objective is to find the structural properties of gallium beryllium trichloride and gallium calcium trichloride. Similarly, we will find elastic properties of this compound as well as electronic and optical properties of gallium calcium trichloride and gallium beryllium trichloride. Now we will talk about the computational work, that what type of work is carried out using Win2Gas simulation codes that involves structure generation, initialization, self-consistent field, SCF cycles or structure optimization, and at last calculation of physical properties. Moving on to the result and discussion of our compounds. First of all, we have structural properties. So both of our compound GAXCl3, in which X represent B and Ca, have cubic crystal structure with the lattice constant of 4.2 angstrom and 5.22 angstrom respectively, having a space group of PM3M number 221, and in which the Ga atom is located at a position 000 and B and C is located at a position 0.5, 0.5 and 0.5, or Cl atom is located at each face of the cube, in which their position at this location is 0, 0.5, 0.5, and at this face the Cl atom's location is 0.5, 0, 0.5, and at this space the Cl atom's location is 0.5, 0.5 and 0. Now in structure properties we have optimization process, in which we measure the total energy of the crystal versus volume. So structural properties are predicted using volume optimizations within which the unit cell minimum energy can be gained, which can be achieved by fitting the Birch-Monaghan equation of states. Actually, Birch-Monaghan fit is express the variation of volume versus energy. The unit cell minimum energy can be gained by minimizing the total unit cell energy with the corresponding volume. So at this location we will get the minimum energy of GABECl3 atom, which is minus 6687.09, and this minimum energy versus volume is known as the ground state energy or optimum energy. Similarly, the minimum volume corresponds to the ground state energy is called ground state volume, and here the ground state volume is observed at 666.26. Similarly, for gallium calcium trichloride, we will get the minimum unit cell energy versus volume by minimizing the total unit cell energy versus volume. So the unit cell minimum energy at this location will be observed, which is minus 8001.43. Similarly, the minimum volume corresponds to this ground state energy will be observed at this location, and whose values is 927.28. This is all about the ground state energy and ground state volume. Now look at the ground state parameters, which is obtained by using the volume optimizations. For example, equilibrium lattice constant, bulk modulus, pressure derivative of the bulk modulus, ground state energy and ground state volume. Now if we look at the curves of these two graphs, here the optimization curve is sharper than the first one. So the compound having sharper optimization curves will have more structural stability as compared to the compound having less sharper optimization curve. Apart from that, a compound having more ground state energy will have more structural stability, and a compound having less ground state energy will have lesser structural stability. The estimated parameters comprise of ground state lattice constant, bulk modulus, pressure derivative of the bulk modulus, ground state volume, as well as ground state energy of these two compounds, as shown in the table, in which the lattice constant of gallium beryllium trichloride is 4.62 and gallium calcium trichloride is 5.22, which is greater than the gallium beryllium trichloride. Similarly, the bulk modulus for the first compound is 44.19 and for their second compound is 84.86. Now the pressure derivative of the bulk modulus for gallium beryllium trichloride is 4.3, and for GaCsL3, which is gallium calcium trichloride, which is 5.99. Similarly, the ground state energy, which is very important for both of the compound, for gallium beryllium trichloride, the ground state energy is minus 6687.09, and for GaCsL3, which is gallium calcium trichloride, the ground state energy is minus 8001.43. So these two values are very important. Now the ground state volume for both of these compound is also quite important. For GaBACl3, the ground state volume is 666.26, and for gallium calcium trichloride, the ground state energy is volume is comparatively higher than the gallium beryllium trichloride. Moving on to the elastic properties. So elastic properties, for elastic properties we use IR elast package, which has been used to calculate the elastic parameters and elastic constant. Now what is elastic constant? Elastic constants govern the crystal response to the external forces, which is crucial for explaining the elastic properties of a material. Similarly, elastic constants are very important for knowing the information, for knowing about the material stability and toughness. The computed elastic constant for these two compounds having cubic crystal structure is shown in the table. So for the first compound GaBeCl3 and for second compound these elastic constants are given. So let's have a look at C11 value for gallium beryllium trichloride, which is 56.80, and for gallium calcium trichloride the C11 value is 74.42, which is higher than the gallium beryllium trichloride. So we can say that a compound having greater value of C11 value will have more harder. So gallium calcium trichloride is harder than gallium beryllium trichloride. Now C12 value for the first compound is 37.95 and for second compound is 14.41. Similarly, for the first compound C44 value is 34.82 and for the second compound C44 value is 7.87. Now for the cubic crystal structure we have only three independent elastic constants, C11, C12 and C44, but for non-cubic system we will have more elastic constant. Now let's talk about the elastic parameters. So the bulk modulus B, the anisotropy A, the shear modulus, the Young modulus, the Poisson ratio, the BG ratio, these are the elastic parameters. So we will talk about one by one. So the bulk modulus for the first compound is 4.30 and for the second compound is 5.99. Now the anisotropy. So anisotropy is a value of critical value is any value other than 1. So a compound having an isotropy 1 will be considered isotropic. So for anisotropic, a material must have a value greater than 1 or lesser than 1 but not equal to 1. So both of our compounds observe the non-unitary value, which is 3.69 and 0.26, which is not equal to 1. So both of our compounds are anisotropic in nature. Similarly, for shear modulus, the first compound gave us the value of 20.70 and the second compound gave us the 13.71 value. The Young modulus for the first compound is 53.71 and for the second compound is 39.02. Now the Poisson ratio. So the critical value of Poisson ratio is 0.26. So for a compound having value greater than 0.26 will be ductile, and for a compound having value lesser than 0.26 will be considered as brittle. So we know that here our compounds give us the value of 0.29, which is greater than 0.26, and 0.42, which is also greater than 0.26. So both of our compounds are ductile, not brittle. Now moving on to the BG ratio or PUGH ratio. The critical value for the BG ratio is 1.75. So for a compound having value greater than 1.75 will be considered more ductile, and for a compound having BG value or ratio smaller than 1.26 will be considered brittle. So we have seen that for both of compound our value is greater than 1.75. So we can say that both our compound is ductile in nature. In other words, we can say that the BG ratio, the Poisson ratio, and Cauchy pressure. Cauchy pressure is actually the difference between C11 value and C44 value. So the difference of C11 and C44, if it give us the positive number, so we will consider the compound as a ductile. But if the difference of C11 and C44 give us a negative value, so we will consider that type of compound a brittle and will not be ductile in nature. So in summarizing our elastic properties, we can say that both of our compound is anisotropic, ductile in nature, and possess high resistance to cracks. So using these elastic properties, we surely deem its application in many modern technologies. We can find elastic parameters like anisotropy, Young modulus, Poisson ratio, and shear modulus by using the these equation. Anisotropy is equal to 2 times of C44 divided by C11 minus C12 value, so it will give us anisotropy. Similarly, if we plug the value of these elastic constant in this equation, so we will get elastic parameters for the rest as well. One thing which I need to mention here is, for mechanically stable cubic structure, we have some constraint on the elastic constants C11, C12, C44, and as well as elastic parameters such as bulk modulus. So if these conditions are obeyed, then we will have a mechanically stable structure. For example, the bulk modulus value should be greater than 0. The C11 minus C12 value should be greater than 0. Similarly, C11 should be greater than 0, C44 should be greater than 0. So these are the conditions for mechanical stability of the cubic structure. Now the electronic properties. So we measure the energy band gaps and density of the states to find the electronic properties of the material. For finding the band structure, we use the modified Becker-Johnson potential to resolve the underestimation of generalized gradient approximation and local density approximation in the band gaps of semiconductor and insulator, due to their shape, which is not fundamental enough to reliably replicate both the exchange and correlation energy and its charge derivative. So here we will use modified Becker-Johnson potential instead of generalized gradient approximation. If we look at the plot of gallium beryllium trichloride, we have energy on vertical axis, which is from minus 14 to 8 electron volt, and at 0 electron volt energy we have horizontal dotted line, which is represented as Fermi energy. The bands which coincides below the Fermi energy is called valence band, and the bands which lies above the Fermi energy is called the conduction band. Here we have seen that the valence band maxima and the conduction band minima both lies at different symmetry point. The valence band maxima lies at the X symmetry point, whereas the conduction band minima lies at the T symmetry point, which shows the indirect band gap of 3.03 electron volt, right? On the other hand, if we look at the gallium calcium trichloride plot, we have the valence band maxima at X symmetry point and the conduction band minima is also at the X symmetry point, which show the direct band gap of 4.9 electron volt and is direct in nature. So the electronic behavior of our first compound GABECl3, which is gallium beryllium trichloride, is semiconductor in nature, because the energy band gap is 3.03 electron volt. But for the gallium calcium trichloride, our band gap is 4.9 electron volt, and which is insulator in nature or somehow dielectric in nature. Moving on to the density of the states. Density of states actually shows the contribution of different electronic states to the valence band and conduction band. And in density of states, we actually shows the total density of states and partial density of the states to know about the electronic structure deeply. If we look at this figure, in which we have the energy ranges from minus 8 to 8 electron volt, and at 0 electron volt energy we have a vertical dotted line which represent the Fermi energy. So the part of the density of the states to the left of the Fermi energy is considered as a valence band, and the part of the density of the states to the right of the Fermi energy is considered as the conduction band. When examining the gallium beryllium trichloride plot, we have seen that there is a dominant contribution of Ga atom and chlorine P states and chlorine F state, and of course the total density of the states of GABECl3, which is represented by the red color, the blue color, and the chlorine P states is represented by the purple color here. So in the valence band, the dominant contributions come from the Ga, Cl3P states and Cl3F states, while there is a minor contribution of GA and ClP states and ClF states in the conduction band as well for gallium beryllium trichloride. Similarly, for gallium calcium trichloride plot, we have a dominant contribution from. It is clear that the dominant contribution in the valent bands come from the GA state and the GAF state, while in the conduction band a minor contribution is observed from the GA atom and the Cl3p states. Now, optical properties. In optical properties, the first one is dielectric function. So the whole reaction of a material to an exposed electromagnetic radiation is described by the dielectric function. The dielectric function is represented as epsilon omega, which is equal to the epsilon 1 omega plus iota epsilon 2 omega. Here the epsilon 1 omega is responsible for the polarization effect in the material and is called ideal dielectric constant, where the E2 omega represents the heat dissipation within inside the material, especially in the dielectrics, right? Now looking at the graph, the optical response is shown in the energy range of 0 to 13 electron volt. For GaBeCl3, the ideal dielectric constant maximum peak is observed at 8.06, having energy 4.64 electron volt. While for GaCl3, the ideal dielectric constant maximum peak is observed at 6.53 and having an energy of 5.43 electron volt respectively. So this is about the ideal dielectric constant maximum peaks. Now we will discuss about the static dielectric constant, which is observed at 4.0 for gallium beryllium trichloride, and for gallium calcium trichloride it is observed at 2.65, right? And looking into the graph, if we applied electric field, then the polarization increases. During polarization there is a friction between electrons, and due to this friction heat is generated because the electron is exerting pressure on each other, and on the other hand the energy is increasing. So due to this energy increase, the frequency of the electron increases, and if the frequency of the electron increases, then electron get less relaxation time, and as a result heat is generated, and due to this heat dissipation or generation, the lag in the polarization occurs, and it is shown here. So we can say that the ideal dielectric constant is basically the polarization of the material. Moving on to the imaginary part of the dielectric function, for GaBeCl3 the E2 omega spectra is observed at 6.29, having an energy of 5.52 electron volt, but for GaCsL3 the E2 omega spectra is observed at 5.71, having energy of 5.92 electron volt. These E2 omega peaks are also called threshold energy or basic absorption edges, because the direct optical transitions within the highest valence band and the lowest conduction band occur here. Apart from that, we can say that the E2 omega is basically related to the heat dissipation within the material. So when we increase the energy of the system, there is a heat generation in the material because of the friction inside the material during polarization. These two materials also satisfy the Penn model, which states that if the band gap energy of the material is lower, then the static dielectric constant of this material will be higher. So if we look at the GaBeCl3, the band gap energy of GaBeCl3 is 3.03, which is smaller than the other compound. So this compound have a greater static dielectric constant, which is 4. On the other hand, if we look at the GaCsL3 band gap, which is 4.9, which is higher than the GaBeCl3, the static dielectric constant of the GaCsL3 is smaller than the GaBeCl3. So we can say that both of these compounds satisfy the Penn model as well. The other optical property is refractive index. So refractive index is actually crucial in determining the refraction of light within the material. So to employ optical material as a photonics or optical devices, it is necessary to understand the refractive index, which is represented by neta omega. It is clear from the figure that for GABACl3 the maximum refractive index of 2.89 is observed at 4.64 electron volt, but for CaCl3 the maximum refractive index of 2.61 is observed at 5.48 electron volt, and the static refractive index of 2.0 is observed for GaBCl3 and static refractive index of 1.6 is observed for GaCaCl3. So we can say that higher the refractive index of the material, the light will travel in it slowly. So due to this slow movement of the light inside the material, the light will change its directions many times, and due to this change in direction, the high refractive index material are very advantageous for the fabrication of lenses, because in lenses, if we have higher refractive index material, for lenses if we have higher refractive index material, then the light will easily bend inside the lenses, which allows the profile of the lenses to be lower. As a result, the thickness of the lenses will be reduced, and the weight of the lens will also reduce. So this is the demand of the modern electronics, that each generation of electronics should be smaller and effective than the previous one. So higher the refractive index of the material, the lower will be the lens thickness and will be applicable or and will have some sort of application in fabricating lenses, right? Now imaginary part of the refractive index, we can also call it an extension coefficient, or it is represented by kappa omega. Extension coefficient is a measure of how much light is being observed at a given wavelength. It is clear in the figure that for GaBACl3 the highest medium absorption of 1.62 occurs at about 12.78 electron volt, while for CaCl3 the highest medium absorption of 1.39 occurs at about 6.2 electron volt. The another optical property is absorption coefficient, which states that how much light or electromagnetic radiation is being absorbed by the material when the light enters through it. It is clear from the figure that an active absorption of 230.51 per centimeter is observed at 13.186 electron volt, right? And for GaBACl3, and for GaCaCl3 the active absorption of 187.23 at about 13.42 electron volt. Moreover, the threshold point for GaBCl3 is observed at 3.03, and for GaCaCl3 the threshold point is observed at 4.9 electron volt, which is consistent with the band gaps of the both of these compounds. So it is proved from the absorption coefficient as well. The threshold point is actually a point at which the absorption of the material began, or in other words we can say that the material can observe an electromagnetic radiation at this threshold energy. The other optical properties of this compound is reflectivity. So reflectivity is actually the amount of light being reflected from the surface of the material. So the optical characteristics or the optical properties have a crucial involvement in the study of the compound surface structure. It is clear from the figure that for GaBACl3 the maximum reflectivity is observed at 0.38, and for GaCaCl3 the maximum reflectivity is observed at 0.26 respectively. So these are the low values in these materials. Moreover, the zero frequency reflectivity for GeBECl3, it is observed at 0.10, and for GaCaCl3 zero frequency reflectivity is 0.05. And if we look at the low energy range, the reflectivity is very low in the low energy range. So it indicates that at low energy range the material act as a transparent material, right? Or we can say that for incident light, the material act as a transparent. So this transparency is actually indicate that these materials are a good or potential choice for fabricating lenses. Conclusion: with the help of Win2K, we employed density function theory to determine the structural, optical and elastic properties of gallium-based fluoroperovskite materials, and it is discovered that the structural properties of both of these compounds are cubic and stable, having an optimized lattice constant of about 4.6 angstrom for GaBeCl3 and 5.2 angstrom for GaCsL3 respectively. We computed the elastic properties using the IR-Elast package to determine the Young modulus, anisotropy factors, Poisson ratio, bulk modulus, elastic constants, PUGH ratios. From these elastic properties, it is investigated and concluded that our compounds are anisotropic in nature, ductile and mechanically well stable. Other than that, the band gap energies and optical properties are investigated with an energy range of 0 to 13 electron volt, and it is observed that these materials are a potential choice for anti-reflection coating and lens creation. So we can say that the relevancy of these materials are anti-reflection coating and lenses creation. The future plans are we will find the magnetic properties of these compounds along with the thermoelectric properties using the Win2K package via density functional theory.